Hi, everyone. Thanks for having me. My name is Alex Wise. I'm a postdoc at Penn State, and I'm working with Varisha and Ian, who are data scientists at JPL on this project that I'll be telling you about here. So why deep learning? Well, the real reason is I was standing next to a guy named John Callis at the NUID pre-ship review 3.5 years ago in the lunch line. And I told him that I thought this would be an interesting project. And he was, the reason I told him that was he was wearing a suit that was probably worth a month's worth of my paycheck. So thought it couldn't hurt to pitch the idea. And 2 months later, he emails me that there's a data scientist at JPL that's interested in working on this type of work. So that's how we got started. This is an approach overview. A couple things I want to highlight are that we're injecting planetary signals into HARP's North solar data here. So we're doing this at the time when you shift to the heliocentric frame, or if you're, if we're doing this to another star, it'd be when you shift to the barycentric frame. And that's important because it sort of minimizes any impact that, reinterpolating or anything like that could have on the data. And then we're feeding these extracted 2D spectra, which have been normalized and interpolated onto a common wavelength grid directly into the network. And unfortunately, we can't feed the entire spectrum in due to computational limits. So for dimensionality reduction, we initially tried PCA. We ended up using subsets of lines for that. And the neural network that we settled on is the convolutional neural network. And I'll talk about how we use that later on here. So for the injected RVs, we're just injecting a uniform random distribution from -1,000 to 1,000 meters per second, 80-10-10 training, validation, and test splits. And we're not using the same spectrum for training, validation, and test. Obviously, we're applying 60 different RVs to each spectrum. That's important because it helps increase the size of our training data and mitigate over training. So we're asking it to learn 60 different RVs for each spectrum. Then and by the way, there are 35,000 of those spectra, those HARP's North solar spectra that we're using. So, one of our initial approaches with the CNN was to use an ensemble of CNN. So we use one CNN per spectral line, and then use ordinary least squares regression to fit for weights for those lines and get the average RV that way. In the top left plot, you'll see that most of those coefficients ended up being really close to 0. So we ended up iteratively pruning that list down to 1,000 lines, and we found that those were a lot more informative for measuring the RVs. So we have our 1,000 line ensemble, 1,000 CNNs combined with this ordinary least squares regression approach. And then we further prune that list down. So that's the plot on the left here. This is just the distribution for visualization and depth wavelength space on the left. And then we further prune that down to 250 lines. That's the plot in the middle. And then on the right, those are just the 250 lines with the lowest RMSE of the single line CNNs. So those are 3 sort of line subsets that we considered here. Then we were able to take, the reason we went down to 250, even though, as you can see from the table of RMSE here, it actually goes up when we go from the ensemble, our test RMSE actually goes up when we go from the 1,000 lines to the 250 lines, is that we wanted to try throwing all the lines simultaneously in a single multi-line CNN. And 250 was about the best we could do with the machine that we were working on without it taking too long. So you can see that we're sort of improving things a little bit in the case of 250 lines by just feeding those directly into a multi-line CNN instead of having 250 individual line CNNs that we fit with the linear regression. So then, all right, so these are all benchmark sort of model results using those -1,000 to 1,000 uniform random injected RVs. And then we thought, okay, let's test this on some actual planets. So this is the planetary grid that we've tested it on so far. We want to fill this in more, but we just did a 1 meter per second at various periods and a 50-day period, various amplitude planets. So we only use these planets for the test data set. So that 10% of the data that we reserved, we injected these planets into that. And these are the results that we got in terms of the period and amplitude. I'll talk a little bit about how we got these in the next slide, but I guess the takeaway here is that we're able to find all the periods to within several days here, or within a few days, and the amplitudes were able to recover really well, except down to about 10 or 20 centimeters per second, which is, I think that's pretty good for the HARPS North data, but we have a lot of work to do in terms of how we do this. So this is what we're doing right now. We're just doing sort of this old school, make a Lomskargel periodogram, fit it with a Planet Plus noise models. This is where we bring in a code called Radial that sort of does all this for us. And this is the 1 meter per second, 250-day period planet. So we're just feeding in guesses, the guess period being this period for the Lomskargel periodogram. And then this is the 20 centimeters per second, 50-day period planet. So those are two of our best planets that we were able to recover using this procedure. But we want to improve upon that. And in particular, we want to focus on, what do we mean when we, oh, wow, I've raced through that. Okay, well, I guess we'll have a lot of time for questions. What do we mean when we talk about quantifying the results of a radial velocity measurement method? And I highlighted, I think injected planetary mass error is one that hopefully we can use in the future to do that. I think RMSE has a sort of a nice, quick and dirty metric for measuring radial velocity error, but it doesn't really translate between methods and doesn't really tell you anything about how detectable the planet is. So, so I want to just plug that idea. And then for the audience, go and check out Varisha's poster if you see what we're hoping to do with this next. We're also working on another project which we hope to use to improve these methods. And you can see more about that at her poster. And we have a paper in prep. We want to test the planet period. Oh yeah, we want to fill in that plot I showed. We want to fill in this plot, obviously, with more amplitudes and periods. Refine our CNN architecture and hyperparameters. Scale it up using a supercomputer and adapt it to newer data and other stars. And then these are some acknowledgements, and I'll leave that up while I take questions. Thank you.
Great. Any questions for Alex?
Thanks a lot, Alex. One question. So you said at the beginning that you were not injecting the spectra themselves, but the PCA. Can you go a little bit more into the details?
Yeah,
please?
so for dimensionality reduction, initially, sorry, I really raced through this faster than, so I probably skipped over a few things. Yeah, so for dimensionality reduction, initially we did use PCA, but we found that it didn't work very well. And so we ended up using the pixels of selected spectral lines as our dimensionality reduction. So we're just, instead of all the pixels in the normalized order by order spectra, we're just going down to pixels of selected spectral lines for our dimensionality reduction.
Okay, because somehow you saw that when you were putting the continuum, it was just what you had no velocity information there. So perhaps you just add noise and that's it. I don't know.
So, sorry, what was that last thing?
If you take the full spectrum,
Mm-hmm.
you will have a lot of continuum, mainly for the sun.
Yeah.
And I suppose you just have noise there and no radial velocity information.
Yeah,
so
I think that noise was confusing the neural network as it was trying to learn. Yeah.
Thank you.
Thank you.
Hello, thank you for the talk. So using this method, how can you estimate the uncertainties in the radial velocities, and how can you be sure that they are realistic? Yeah,
so the network does not give, thank you for the question. The network does not give us uncertainties, it gives us radial velocities. And I think that is a limitation. I don't know if there's a way, it's beyond my area of expertise to know if there's a way to, I'm the sort of EPRV pipeline side of things, but I don't know if my colleagues would be able to answer that better. You can talk to Varisha at the poster session. If there's a way using neural networks to estimate their own uncertainty. But I think that really brings me back to what we can do with this method, which is we can quantify the injected planetary mass error, right? So we get some radial velocities out, and then we can fit for the mass according to some model, and then we can look at how what the error on that mass is, and I think that's maybe the best way to do it. What was the second part of the question? Sorry, I forgot.
So just as a follow-up, so how can you fit the planetary mass if you don't have uncertainties in the radial velocity measurements? Do you assume that they have all the same measurement error to do a Keplerian fit?
I don't know. Let's talk about it afterwards. Sorry, it would take me too long to come up with a smart answer right now. So, thank you. But yeah, I'll talk afterwards. Anyone else?
Hello, thanks for the talk. I wonder what's your loss function to train the neural network? Do you just simply ask for a recovery of the injected RV?
Yeah, it's just the I think we're using the RMSE right now for the on the full 60 injected RVs. We're using that for the loss function right now.
So does it somehow imply that you assume you know the true reference spectrum? Because if your reference spectrum is contaminated by some random, say, planetary RVs, then does that?
So we're working with the sun, so we do know the true reference. But you're right. That adds a complication when we go to other stars, and we're thinking about ways to work on that. But for now, this is sort of an experiment only using solar data.
Thank you for the answer. Great talk.
Thanks.
Great. Let's thank Alex again.